Yeah, so hello everyone. I'm Rakshit Naidu. I'm a final year student at computer science student at Manipal Institute of Technology. This project is called DPixel, uh, where we worked on a small package for making computer vision and deep learning simpler for beginners. Worked on was explainable AI using CAMs. So what CAMs are actually? Uh, CAMs are called class activation mappings. So they're denoted as linear combinations of the weights of the neurons in the last layer before the gap layer with the activation maps itself. So I intended to add some well-known implementations of CAMs like GradCam, GradCam++, Smooth GradCam++, SSCam. Yeah, so the CAMs that I added in PyTorch were the following. I added the original CAM implementation, GradCam++, Smooth GradCam++, ScoreCam, and even implementation in DPixel. And yeah, I'll be talking about our paper as well, that is SSCam. So right now, this is a paper that is under review at ICPR 20, SSCam. Um, and a motivation was that the score cam wasn't working very well in some of the images because it's quite noisy by itself because of the really non-linearity, and this is what encouraged us to tackle the issue. We developed two variants of SSCam, where the first one was we apply the smoothing operation before the normalization, and in the second one we apply the smoothing operation after the normalization with the input mask itself. And this is the SSCam pipeline. So what we do is we have an input and we pass it through the particular convolutional neural network. And once that's done, we upsample it to a particular size. And once that's done, we take those activation maps and uh, multiply them pointwise with the input itself to create uh, input mask. And once that's done, we add some Gaussian noise to the uh, input masks itself, and uh, and then we take the average scores of all the that we generate and we linearly combine them in the end with the upsampled activation maps to produce the output. And why do we add noise? The reason that we add noise is that noise is added to smoothen out the image, and we capture more features in this process. And we actually borrow this idea from the smooth grad paper. Uh, Gaussian noise is actually better than the noise sampled from a uniform distribution according to our experiments. And Gaussian noise also masks the irrelevant features captured if you see the pipeline closely out here. In visual comparison, we also perform better than uh, the existing CAM techniques like GradCam, GradCam++, Smooth GradCam++, and even ScoreCam. You can see that SSCam 2 performs really well. And in terms of evaluation metrics, uh, insertion and deletion curves, these are the graphs out here for the black and tan coonhound maps that we generated as shown before here for these maps. And we conduct faithfulness evaluations where we calculate the area under the curve scores for deletion and insertion curves, where for deletion curves the lower is the better, and for insertion curve higher is the better. And once that's done, we see that SSCam 1 actually gives us good results. Even with average drop and average increase in confidence, uh, with VGG16, we actually get good results with SSCam 1. And even with localization evaluations and human trust evaluations, we perform better than the existing CAM techniques. with 3 different networks that we evaluated on: VGG16, ResNet 18, and then SqueezeNet 1.0. And that's it for now. A future contribution is that we are working on a paper on combining integrated grad and ScoreCam. We hope that it would be out by the end of next month. That's it from my side.
So guys, if any of you is having any questions regarding the presentation, you guys can ask now.
So anything you want to say about saliency maps for activations, for knowing which regions are contributing towards the output of the image instead of camps?
Sorry, could you repeat that?
Yeah, my question is, have you tested out using saliency maps instead of camps?
Uh, yeah, actually, saliency maps are just feature maps, right? And we try to enhance these feature maps using camps. That's what we do.
Okay, great.